Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chatterjee, and a warm welcome back to my channel. Before we dive in, a quick note for my non-civil engineer viewers: while we'll be tackling some technical concepts today, please feel free to follow along. Simply treat the engineering terms as numbers and focus on applying the Excel process to your own DIY spreadsheet projects. In my last two videos, we thoroughly covered the theoretical aspects and the design of a doubly reinforced beam for bending stress, first through a detailed PowerPoint presentation, and then applying it in Excel. Today's video, titled Shear Stress in Doubly Reinforced Beam, IS 456 Part-03, is an Excel presentation, and a perfect DIY project, especially for my fellow civil engineers. If you're new to the channel, I highly recommend checking out Part 1 and Part 2 of the series first. And for an even stronger foundation, my IS 456 Singly Reinforced Beam Design, Bending Moment, Shear Force and Deflection Limits and Checks in Excel, series, Parts 1 through 7, will be incredibly helpful. In this episode, we're going to dive into several critical shear stress calculations in Excel. To help us visualize the tasks ahead and recap the necessary steps for shear design, let's now move to our next slide. Alright. Now, we're seeing the slide titled Steps for Shear Design for Doubly Reinforced Beam. We're at the starting point of this discussion. And right at the beginning, I want to reiterate that the steps for shear design in a doubly reinforced beam are, more or less, the same as for a singly reinforced beam. I've already explained this in detail in my video series, Excel for IS 456 Beam Design, Solving Shear Stress Problems, Parts 2 and 3. For the sake of recapitulation, let's quickly go over these essential steps. First, we calculate the nominal shear stress, tau v. This is simply the factored shear force, Vu, divided by the effective cross-sectional area, B multiplied by D. This calculation remains identical for both singly and doubly reinforced beams. Next, we determine the design shear strength of concrete, tau c. As per IS 456, 2000, Table 19 provides these values based on the concrete grade and crucially, the percentage of tension reinforcement, calculated as 100 multiplied by AST divided by the product of B and D. Then, we consider the maximum shear stress, tau c max. Table 20 of IS 456, 2000 specifies the maximum permissible shear stress for different concrete grades. Remember, your calculated tau v must never exceed tau c max. If it does, you must increase the beam section size. Finally, for shear reinforcement, or stirrups, if tau v is greater than tau c, stirrups must be provided to resist the excess shear force, VUS. This VUS is calculated as VU minus VUC, where VUC equals tau c multiplied by B multiplied by D. The spacing of these stirrups, SV, is then determined based on their area, ASV, the steel's yield strength, Fy, and the VUS value. And critically, even if tau v is less than tau c, minimum shear reinforcement is mandatory, as per IS 456, 2000, clauses 40.3 and 26.5.1.6. This is vital for ensuring ductility and preventing sudden, brittle failure. Alright. Now, the question is, where is the slight variation in the results when dealing with a doubly reinforced beam? In a singly reinforced beam, we generally don't provide steel beyond the permissible limit, PT limit. However, in a doubly reinforced beam, we are often bound to provide additional tensile steel, beyond PT limit, precisely to accommodate that extra bending stress. And here's the crucial link: we know that the design shear stress, τc, is directly proportional to the percentage of tension steel provided. Therefore, during the calculation of design shear stress, τc, for a doubly reinforced beam, because it typically has a higher PT, you will generally find the value of τc to be on the higher side. But, yes. Here is a but. In the case of shear design for a doubly reinforced beam, we often initially try to minimize the section, by reducing the depth, or width, or both. Since compression steel allows for smaller dimensions for the same moment capacity. As a direct result of this, the effective cross-sectional area, B multiplied by D, of the section will be less than what a comparable singly reinforced beam might require. We also know that the calculated nominal shear stress, tau V, is inversely proportional to this effective cross-sectional area. Hence, a smaller area means tau V will tend to increase. So, in summary, you have two opposing effects: a higher τc due to more tension steel, but also a potentially higher tau V due to a reduced section size. By balancing these two factors, we then proceed with our shear design. Alright, let's move over to the next slide. Welcome back. We're picking up right where we left off, on our Excel sheet where we completed the design calculations for bending stress in a doubly reinforced beam. If you recall, that was covered in our previous presentation, bending stress in doubly reinforced beam. IS 456, Part-02. This Excel sheet serves as our foundation. Today, however, we're shifting our focus. We'll be using this same doubly reinforced section to solve for shear stress, right here in Excel. I truly hope you find this episode insightful and enjoyable. As always, your feedback and questions are incredibly valuable, so please don't hesitate to leave them in the comments below. You know, back in our childhoods, especially here in West Bengal, a thumbs up meant nothing. We used to say Labo Donka with this symbol. But today, for us YouTube freelancers, it's a great achievement. What a metamorphosis of symbol with the change of continents. So, if you find this video helpful, please do give it a big thumbs up, share it with your colleagues and friends who might benefit, and most importantly, remember to subscribe for more valuable content like this. Thank you so much for your continued cooperation and support. Now, let's transition to the original Excel sheet to begin our new calculations. Alright, we're now on the actual Excel sheet, and as you can see, we're looking at the very same dashboard we've used before. Below this, we're going to dive straight into designing the same beam for shear. First, I want to introduce you to the specific tasks we'll be performing in this DIY project. Think of these as our step-by-step roadmap. The tasks are as follows. Preparation of our new heading for shear calculations, which will be within the merged cell A13 to E13. Then, we'll apply conditional formatting to that heading. Next, we'll set up conditional formatting for the ultimate shear stress, located on cell H3, which we'll name VU. Following that, we'll calculate the area of steel provided for shear, on cell G6, named ASV. And yes, we'll also apply conditional formatting for ASV on cell G6. We'll then move to the preparation of our case type. A crucial cell we'll name case_type. And naturally, conditional formatting for case type will follow. Then comes the preparation of our condition, within the merged cells G13 and H13, which we'll name condition. You guessed it, conditional formatting for condition as well. Next, we'll prepare the beta value, found on cell C15, named beta. Followed by the preparation of designed shear stress, on cell D15, named TC. Then, the preparation of calculated shear stress, on cell E15, named TV. And we'll apply conditional formatting for TV. After that, we'll prepare the maximum designed shear stress, on cell F15, named TC_max. Then, the differences in designed shear stress and calculated shear stress, on cell G15, named VUS. And finally, the preparation of spacing of the stirrups, on cell H15, which we'll name SV. Now, I know this list seems very, very long, but don't worry. By the end of this video, after we've gone through each step together, you will truly be a master of shear design. Task number 1. Preparation of our new heading for shear calculations. I will start with this point. To do that, please see the formula in the formula box, which I have developed for your clear vision. The formula for the merged cell A13 to E13 is, equals to, if, open parenthesis, check_03 equals to, OK, in quotation marks, comma, shear stress calculation, in quotation marks, comma, shear stress calculation, within first bracket, bending check prerequisite, within quotation marks. Close parenthesis. The simple meaning of this formula is, if, check_03 equals to, OK, then type shear stress calculation. Otherwise, type shear stress calculation, plus, within first bracket, bending check prerequisite. Now, by copying this formula from the formula box, I am pasting it onto the merged cell A13 to E13. Since our check_03 equals to OK, we are watching the heading, shear stress calculation. Now, for the time being, I am deleting the formula from cell H11. That is the final check for bending stress, or check_03. As a result of this, we are seeing shear stress calculation, plus, within first bracket, bending check prerequisite, as our heading. Now the question is, why is this heading shear stress calculation, tagged with bending check prerequisite? Because we know that for shear stress calculation, the percentage of tension steel, or PT, has a main role in the calculation of designed shear stress, or tau c. Without calculating the value of tau c, we cannot proceed to the next step of the design. Now, by undoing, I am retrieving the formula for check_03, and once again, we are seeing shear stress calculation as a heading. So, we found our formula for the heading is functioning properly. Task number 2, conditional formatting for that heading. As a structural designer, sometimes I found that I forgot to put some important data in my calculation. Then I start to fumble, asking, what happened? To minimize this fumbling, I use some color as a warning, and as well as a reminder. First, follow the simple formula that we have to use during the conditional formatting. And the formula is, equals to, open parenthesis, check underscore 03 equals to, OK, in quotation marks, close parenthesis. This is actually a true or false function. If Excel find check underscore 03 equals to OK, then conditional formatting will perform some special work for us, by changing the fill color of the cell, or font, or both. First, I am selecting yellow as a primary base color of the cell. Now, for conditional formatting, copy the formula from the formula box. Then, from the ribbon, select the option for conditional formatting. Select New Rule. Then, from the menu list, select the option, Use a formula to determine which cells to format. Then, in the dialog box, paste the formula. Now, select Format option. Then select the option Fill, and select the green color as a fill color. This green color for the cell will be activated when the provided logic is true. Presently, our logic, check underscore 03 equals to OK, is true, hence we are seeing the green fill. Now, once again, for a time being, I am deleting the formula from the cell with the heading Final Check. As a result of this, now our heading field is filled with yellow color. That reveals the success of our mission. By undoing, I am returning to the previous position. Task number 3, Conditional Formatting for Ultimate Shear Force, VU. Is it possible to find a beam without shear force? I think no. What do you think? First, study the formula that I am going to apply for the conditional formatting for VU. The formula is, equals to, open parenthesis, n, open parenthesis, check underscore 03 equals to, OK, in quotation marks, comma, VU equals to 0, close parenthesis for the inner condition, close parenthesis for the overall condition. Once again, this is a true or false function. The application of the and function makes this formula more critical. The simple meaning of this formula is, if check underscore 03 is OK, but the value in VU is equal to 0, then only the condition will be true, and conditional formatting will be activated. Now, for the application of the conditional formatting, copy the formula from the formula box. Next, select the cell H3, or VU. From the ribbon, select the option for conditional formatting. Select New Rule. From the menu list, select the option, Use a formula to determine which cells to format. In the dialog box, paste the formula. Now, select the Format option. Select the option Fill, and select the yellow color as a fill color. To accept this condition, click on OK and then Apply. This yellow color for the cell will be activated when the provided logic is true. Presently, our logic, check underscore 03 equals to OK, and the value in the cell VU is 0. Hence, the applied logic is true, and we are seeing the yellow fill. Finally, by selecting the cell VU, choose the no fill option for the normal condition. That is, when check_03 equals to OK, and the value in the cell VU is greater than 0. Now, I am changing the value of VU from 0 to 50 kN. See the cell now, without any fill. Task number 4, for the calculation of area of steel provided for stirrups and links on cell G6. By using the Define Name option in Excel, I have provided a name for the cell as ASV. Just above ASV, on cells F5, G5, and H5, we see dia, 0, mm, legs, 0 no, and links, 0. Here, dia means the diameter of the stirrups and links. Its present value in the cell is 0. Legs, 0 no means the number of legs we are going to use, and its present value is also 0. Remember, the minimum number of legs for stirrups should be 2. If we input the value 4, it will indicate 2 sets of 2-legged stirrups. The minimum number of legs for links should be 1. The present value in this cell is also 0. Here's the formula we'll use. Equals to, if, open parenthesis, n, open parenthesis. Check_03 equals to, OK, comma, or, open parenthesis. dia_03 is greater than 0 and legs is greater than 0, close parenthesis, comma, and open parenthesis, dia_03 is greater than 0 and links is greater than 0, close parenthesis, close parenthesis, close parenthesis. Then, comma, if that's true, we'll calculate, open parenthesis, legs plus links, close parenthesis, multiplied by 0.25, multiplied by pi, that's pi, open and close parenthesis, multiplied by dia_03 to the power of 2. Otherwise, if the initial conditions aren't met, we'll leave it blank, represented by 2 quotation marks with nothing in between, close parenthesis. In simple words, when check_03 equals to OK, and dia_03, legs or links will have some positive value, then Excel will calculate the area of steel, or ASV, otherwise, it will keep the cell blank. Now, by copy and paste, I am pasting the formula on cell G6, and we are observing the value of the cell blank. This is because check_03 equals OK. However, we have not yet provided any values in cells F5, G5, and H5. Let's test this out with ASV. I'm setting dia_03 to 8 and legs to 2. See how the ASV cell now shows 100.53 square millimeters. Now, watch what happens when I add 2 more links. The value immediately changes from 100.53 to 201.06 square millimeters. Next, I'm going to delete the formula from check_03. And just like that, the ASV cell turns blank. I'll use the undo option to go back. Perfect. We're seeing 201.06 square millimeters again in ASV. So, it looks like we're on the right track with our formula. Conditional formatting for ASV. Let's set up conditional formatting for our ASV cell. The formula for this conditional formatting is, equals to open parenthesis, n, open parenthesis, check underscore 03 equals to OK, comma, or, open parenthesis, VU equals 0, comma, VU equals blank, comma, ASV equals blank, close parenthesis, close parenthesis, close parenthesis. Once again, this is a true or false function. The application of the and function makes this formula more critical. Applying the conditional formatting. Now, for the application of this conditional formatting, copy the formula from the formula box. Next, select cell G6, or ASV. From the ribbon, select the option for conditional formatting. Select New Rule. From the menu list, select the option, Use a formula to determine which cells to format. In the dialog box, paste the formula. Now, select the Format option. Select the option Fill, and select the yellow color as a fill color. To accept this condition, click on OK and then Apply. The simple meaning of this formula is: if Excel finds check_03 equals to OK, value of VU greater than 0, and value of ASV greater than 0, it will do nothing, otherwise it will fill the cell ASV with yellow color. This acts as a reminder for providing the value of VU and some steel as a shear reinforcement. Seeing it in action. Since we are watching, check_03 equals to OK, and VU equals to 50 kN. And look, cell ASV turned into a yellow cell. Now I am providing 8 dia, 2-legged stirrups as our shear reinforcement. Once again, the cell ASV turned into a white cell. Now I am deleting the value for VU, value for dia, value for legs, and the formula in check_03. As a result of this, we are seeing all the cells turned into a white cell. So we can say our conditional formatting is in action. By using the undo option, I am returning to the previous position. Task number 6, case_type, condition and table for stirrups. The actual story behind our shear design calculation really lies in two crucial areas, case_type and condition. First, I'm going to reveal the first part of that story, the story of case_type. I have designated cell F13 as our case_type cell. And here's the interesting part: by using the standard cell formatting option, not by conditional formatting, if I put any value into this cell, we will find that the preceding portion of that number will be tagged with case type dash, followed by that number. For example, say I am typing here 1. Look at cell F13. It's now exhibiting case type dash 1. Here, the figure 1 is vital for us. No, we need not to put any value manually in this cell. In actual practice, these figures will be generated automatically in this cell. Table for stirrups. Now, for more clarification regarding case type, I am switching over to the sheet named as table_F. In this sheet, we are observing a table for stirrups. We have to create a table like this. Under the column with the heading case type, we have to type 1, 2, 3, and 4. Under the column with condition, we have to type. For case type 1, tau c max greater than, tau c and tau c greater than or equal to, tau v. Next, for case type 2, tau c max greater than, tau c and tau c greater than or equal to, tau v, plus ductility. The only difference in this statement from the above is, here we have included the ductility detailing options. Next, for case type 3, tau c max greater than, tau v and, tau v greater than, tau c. Finally, for case type 4, tau c max greater than, tau v and, tau v greater than, tau c, plus ductility. Once again, the only difference in this statement from the above is, here we have included the ductility detailing options. Formulas for stirrup spacing. Below this, we are seeing 4 numbers of formulas. These formulas will calculate the spacing of the stirrups, based on the auto-generated case type. First, SV case underscore type equals 1, that is for spacing of the stirrups for case type 1. And the formula is equals to, if, case underscore type equals 1, comma, min, open parenthesis, b, comma, d underscore EFF, comma, open parenthesis, 0.87, multiplied by ASV, multiplied by, FY, close parenthesis, divided by, open parenthesis, 0.4, multiplied by, b, close parenthesis, comma, blank quotation marks, close parenthesis. The simple meaning of this formula is, if our case type is 1, that means when, tau c max greater than, tau c and tau c greater than or equal to, tau v, it will return us the value of spacing SV, in millimeters. This is by following the equation, minimum, among the value of, width b, effective depth d underscore EFF, and, the value of, 0.87, multiplied by ASV, that is, area of the steel provided for stirrups, multiplied by, Fy, or characteristic strength of the steel. And if our case type is not 1, it will keep the cell blank. Now, by copying this formula, I am pasting this in cell C3 of this sheet. Next, SV case underscore type equals 2, the formula for this case type is equals to, if, open parenthesis, case underscore type equals 2, comma, min, open parenthesis, b, divided by, 2, comma, d underscore EFF, divided by 2, comma, open parenthesis, 0.87, multiplied by, ASV, multiplied by, Fy, close parenthesis, open parenthesis, 0.40, multiplied by, b, close parenthesis, comma, blank quotation marks, close parenthesis. This formula is more or less the same as the formula for SV case underscore type equals 1. The only differences in this formula are, we have to consider half the value of B and D underscore EFF. Now, by copying this formula, I am pasting this in cell C4 of this sheet. Now, SV case underscore type equals 3, the formula for this case type is equals to, if, open parenthesis, case underscore type equals 3, comma, min, open parenthesis, b, comma, d underscore EFF, comma, open parenthesis, 0.87, multiplied by, Fy, multiplied by, ASV, multiplied by, d underscore EFF, close parenthesis, divided by, open parenthesis, VUS, multiplied by 1000, close parenthesis, comma, blank quotation marks, close parenthesis. The simple meaning of this formula is, if our case type is 3, that means when tau c max greater than tau v and tau v greater than tau c, it will return us the value of spacing SV in millimeters. This is by following the equation, minimum, among the value of width b, effective depth, d_EFF, and the value of the equation, 0.87, multiplied by Fy, multiplied by ASV, multiplied by d_EFF, divided by VUS, multiplied by 1000. And if our case type is not 3, it will keep the cell blank. Now, by copying this formula, I am pasting this in cell C5 of this sheet. Now, SV case_type equals 4, the formula for this case type is equals to, if, open parenthesis, case_type equals 4, comma, min, open parenthesis, b, divided by 2, comma, d_EFF, divided by 2, comma, open parenthesis, 0.87, multiplied by Fy, multiplied by ASV, multiplied by d_EFF, close parenthesis, divided by, open parenthesis, VUS, multiplied by 1000, close parenthesis, comma, blank quotation marks, close parenthesis. The simple meaning of this formula is, if our case type is 4, that means when tau c max greater than tau v and tau v greater than tau c. Additionally, we are also considering the ductility detailing. It will return us the value of spacing SV in millimeters. This is by following the equation, minimum, among half the value of width and effective depth, and the value of the equation, 0.87, multiplied by Fy, multiplied by ASV, multiplied by d_EFF, divided by VUS, multiplied by 1000. And if our case type is not 4, it will keep the cell blank. Now, by copying this formula, I am pasting this in cell C6 of this sheet. This formula is more or less the same as the formula for SV case_type equals 3. The only differences in this formula are, we have to consider half the value of B and d_EFF. Presently, we are seeing all the cells as a blank cell, because we have not yet put the formula in the cell reserved for case_type. To do that, now I am returning to the sheet, named as design_01. Alright, that wraps up shear stress in doubly reinforced beam. IS 456 Part 03. Today, we successfully completed our dynamically interchangeable Excel sheet for both doubly and singly reinforced beam design for shear stress checks. Instead of adding more time to this video, I'm saving the sheet for the next one. And trust me, when we will complete the sheet, it will work beyond our expectations. Your free Excel sheet. Now, for an announcement many of you have been waiting for, the free Excel sheet I demonstrated previously, the one without detailed explanation. I've received so many fantastic emails, and I'm genuinely thrilled to share it with you. To get your copy, Please read the instructions carefully in the description below this video. It's a quick 2-step process. You'll need to email me your request and leave a comment on this specific video letting me know you've sent it. Both steps are absolutely essential. And once you've got the file, a quick "got it" or "thank you" would be a huge sign of gratitude for my honest effort. You're ready to pay it, aren't you? I definitely believe so. Empower your learning. For this entire beam design series, my main goal is to empower you to build your own Excel sheet. Relying solely on pre-made sheets can limit your understanding. Developing your own truly builds your skills and confidence. If you hit any snags while creating your sheet, remember, I'm here to help you completely free of charge. My focus is always on your learning and skill development. Support my work. If you'd like to support what I do, here are 2 simple ways. Watch my videos in full. Consider a contribution, whatever fits your budget, without any pressure. You'll find the details in the description, and the communication process is the same as requesting the Excel sheet. Your engagement genuinely helps me improve how I share knowledge with all of you. Stay engaged and support the channel. I hope you enjoyed this episode. Please leave your feedback and questions in the comments below. If this video helped you, give it a big thumbs up. Remember, sharing knowledge means enhancing knowledge, so please share this video. And if you want to support my honest effort, subscribing to the channel is the best way to do it. Subscribe for mutual benefit. Thanks for your cooperation and support.